Okay, quantum chemical models. If you start from physical chemistry, there are, and the Schrödinger equation, and the people who teach physical chemistry spend too much time playing around with the Schrödinger equation. It should almost be accepted and go from there. In order to take the Schrödinger equation and get practical models, you need to make three approximations. The first one is called the Born-Oppenheimer approximation, and it's so good that we can ignore it. It says that nuclei move much more slowly than electrons, and so from the perspective of actually doing a calculation, we can assume that the nuclei are stationary. That's a necessary simplification. It doesn't really help solve the problem in a sense. The second one is that we have to restrict the extent to which electrons know about each other. The formal word is correlate. This simply says we can restrict it such that they don't know about each other at all. They're independent, all the way to they know everything about each other. Now, that's the second approximation. I'll get to that in a second. The third one is that we have to say the solutions of the Schrödinger equation, or this approximation to the Schrödinger equation for molecules, is a sum and differences of solutions of atoms. This is called the LCAO approximation. The way to show this is a diagram. The top corner here, we have the solution to the Schrödinger equation. We have two approximations. Again, I'm forgetting the third one. The first approximation is the extent to which electrons know about each other, or the what I'll call recovered correlation. You can recover 100% of the knowledge of electrons about each other, or you can recover not zero, but very close to 0%. Okay, that left-hand column is called Hartree-Fock theory. The second approximation is the representation in terms of atomic solutions. You can do the least expensive thing, which is the fewest number of functions representing an atom, or you can do a large expansion, which is ultimately complete. Okay, in the limit of this left-hand column, it's called the Hartree-Fock limit. It is a theory upon itself, but it's one of many. In the limit of way over here, you have other models, and in the far right, you have the solution of the Schrödinger equation. Now, I can immediately tell you can't get to the far right, but you can get pretty close to it now. If I start, Hartree-Fock models, or Hartree-Fock theory, was the first real theory that was developed. This was postulated first, or developed first, in the early 1950s. It had its high point in the 60s, 70s, 80s, and has pretty much been supplanted by other methodologies now. It still has uses, but it's largely of historical value at this point. I'm not going to say more. What it does allow us to do, since Hartree-Fock theory is simple, it does allow us to explore the other dimension, the other approximation, what's called LCAO. This is in terms of a basis set. What I really mean here is that as I write a molecular solution, I'm going to write it in terms of a set of atomic solutions, and how complicated are those atomic solutions. There is a least complicated atomic solution, which has the number of functions required to hold the atoms, the electrons of an atom, and that's it. That's called a minimal solution. And then there are steps all the way of how do you improve that. Again, I'm not going to go into any details. There's steps how to improve it, but finally you get to the notion of complete. If I make that solution for the atom infinitely flexible, then it's complete, and making more wouldn't make any difference. Diagrammatically, what I'm saying is the following. I'm starting, this is the basis set, or the atomic solution. I'm starting from the simplest possible one, and I can do at least three dimensions of improvement. I can take the minimal one, which is, in the case of carbon, it has a 1s function, a 2s function, and a set of 2p functions. I can take that and I can double it. I can say, well, I've got two 2s functions, two 2p functions, or triple it, et cetera, et cetera. That's called splitting. I can add functions that are higher order. So if I have a px function, I can add some d functions. Those are higher order. Those are derivatives. It's a Taylor series. And finally, I can add functions that are really not associated with the atom. They're far away. They're diffuse. They have very little effect on the atom itself, but on the atom in molecules, they may have a great deal of effect. So there's at least three things I can do to improve or to complicate the choice of atomic basis set. And finally, you get to this point of completeness. Just to illustrate here, there are literally dozens, if not hundreds, of different basis sets from several different laboratories over a period of 30 years or more. Spartan supports them all. Let me just jump into Spartan just to show you what I mean by that. Let's take a molecule. I just build something. I don't care. And I go into here. A very intimidating dialogue. If I jump into a method, I have choices. If I don't like those choices, I have the word more, and it's divided by really author. If I go to here, it's trying to make things simple. In other words, once you've admitted there have to be choices, try to make them simple. Try to make it easy for people to select, and if you really are painful, you can actually type in something. So there are three categories, or there are three sets there. Okay, yeah, go ahead. The original set, when computers were much less capable than they are now, the original developments were trying to make things efficient. And that set I would call the Popel set from John Popel's lab. And these were base sets that were meant to be computationally efficient, probably a factor of 2 or 3 over the competitors. As far as trying to make the most out of trying to make functions that had relationships in them, so you could actually take advantage of them computationally. So these the equivalent of this is a very common one, 631G star. The equivalent of that in a Dunning set, which is another set, is probably a factor of 2 computationally, simply because of the way it's designed. You get to the idea of completeness. There is something called a complete basis set. It's this huge thing which you can apply to little tiny molecules and not very much else. And it's a beautiful concept, because what it allows you to do is to forget about this second approximation, this LCAO, and simply say we're going to worry only about one approximation. We're going to worry about the extent to which electrons talk to each other. The first theories beyond Hartree-Fock theory are now collectively called wave function-based methods. They're very simple. They say that I have a solution which puts electrons in orbitals, in spaces, and it puts, for most molecules, it puts 2 electrons in a bunch of spaces. But left over from the mathematics is a bunch of orbitals, functions, that have no electrons in them. So the solution is really a 2-part solution. It's a set of orbitals which have electrons in them, which define the properties of the molecule, and then everything left over. Now, there is a theorem which says the following: if my basis set is complete, is infinite, which I can't do, but I can dream about, and if I take every electron in one orbital and put it from an orbital occupied to an unoccupied one, I do that for every 1 electron, all possible permutations, and then I do every 2, not pair, but every just 2. And put them in every 2 possibilities, and then every 3 and every 4 and every up to what have you. You'll realize immediately that's a problem, because that's doing every one is a factorial problem, and And because you have an infinite number, it's an infinite factorial problem. So it's completely impossible. If you do that, you've solved the Schrodinger equation. Now, there are a bunch of methods that have been developed, and one is called configuration interaction, which literally does that. It promotes, but it has to stop somewhere. So it stops usually at 2 promotions. And the other one is called Muller-Plesset theory, which is to do exactly the same problem, but do it as in terms of what I refer to as perturbation theory, which says the solution of no promotions is almost there, and we're gonna do a perturbation expansion on what would happen if I were to do all solutions. So this is another approach. Okay, there are 2 classical wave function based approaches. There's a third approach which I refer to as the gold standard. That's called coupled cluster theory. It's sort of a mixture of the 2. And the only thing that I really want to get across is it scales as the 7th power of the number of the size of the problem. If you think about that for a moment, if you take a number, I don't know, 2, and you make 2 to the 7th, that's not so bad. If you take a number 100, this is the number of functions. 100 to the 7th is a big number. If you take a number 1,000, 1,000 to the 7th is a very big number. What this means is that this idealized gold standard method, called coupled cluster theory, is a beautiful concept, and it's a theory that you can actually apply to small molecules, but you can't apply it to anything bigger than maybe 10 atoms. But it raises another interesting point. It raises the point that maybe with enough computer time, we could, if this method is really any good, we could use it to replace experiment. And that's exactly the way it's used now.